Chapter 7, Quantum Mechanical Model of the Atom. The behavior of the very small. We are familiar with the macroscopic world, things that we can see and get our hands onto. So that's what we're comfortable with because that's what we observe. So the large or the macroscopic world. There is another world that is much, much smaller, and I don't mean another planet. There's another part of the universe that's absolutely small, or referred to as the quantum world. We're talking about zooming way in on matter and looking at electrons. Electrons are considered absolutely small. They behave very differently than regular objects like baseballs. What's really weird and disturbing about the absolutely small particles is that they can be in two different states at the same time. Not states of the country, but states of being. If you observe them, though, they have to be in one or the other. But if we're not looking at them, they can be in two states at once. So an unobserved radioactive nucleus could be simultaneously emitting a particle and not emitting a particle. If we observe it, though, it has to be one or the other. So, electrons. Just to get an idea of how small they are. A single speck of dust has more electrons than the number of people who have ever lived on Earth. This makes me think of Horton the Who, right? And he had this little dust particle that he had on the clover, and it was this world and these little people, right? So electrons are incredibly small. Their behavior determines much of the behavior of atoms, and so we have to have at least some basic concept of how electrons behave. Directly observing them is impossible because they're too small. I mean, we can barely get images of atoms, and electrons are much, much smaller. So we can't directly observe them, but we can indirectly observe them. And when we observe them, even indirectly, the behavior of the electron changes. Which, you think about that, it's like, how can that possibly be, right? Is the electron aware of things? Is it a sentient being that it can tell when it's being watched? No, it isn't. There are a lot of things in this chapter that you are not going to understand. And it's okay, because nobody completely understands it. So it is confusing. So there's a thought experiment that's become quite famous involving Schrödinger's cat. And this thought experiment, which did not actually occur and no cats were harmed, demonstrates how quantum strangeness, the behavior of electrons, does not translate to our everyday world. So I've got a couple of videos to help demonstrate this.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I have answer, please?
So the idea there is that you don't know if the cat has died or not until you open the box. So before you open the box, the cat is dead and alive. That's ridiculous, right? It's ridiculous with a large thing like a cat. It's not ridiculous with electrons. So here's another Schrödinger's cat video. Because you just can't have enough Schrödinger's cat videos. These are like educational cat videos on YouTube, right? I hate it when it does that.
Hello and welcome to I Don't Think That Means What You Think. Where we bits of scientific theories that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flaws of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand. So you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding science. And so, there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it while we watch for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. That's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom is decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber and observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Okay, any questions? My son has a great T-shirt. It's a wanted poster. Wanted, dead, and alive. Schrödinger's cat. So, like he said, the point of the Schrödinger's cat thought experiment is that the laws of physics that apply to what we can see do not apply to electrons. And there's no way to mesh the two together. They just don't. And just to make you feel better about being confused about all of this, Niels Bohr, who's one of the guys that worked on quantum mechanics, said, anyone who is not shocked by quantum mechanics has not understood it. It's just a shocking idea. Schrödinger, the guy with the cat experiment, said, I don't like it, and I'm sorry I ever had anything to do with it. Albert Einstein, attempted unsuccessfully to disprove quantum mechanics until he died. He couldn't, but he didn't like it either. Nobody liked it because we can't understand it. But that doesn't mean it isn't there. So, the quantum mechanical model explains how electrons exist and how they behave in atoms. And it helps us to understand and predict the properties of atoms that are directly related to the behavior of the electrons. These sorts of things include why some elements are metals and others are nonmetals, why some elements gain one electron when forming an anion and others gain 2 electrons. Why is that? Quantum mechanics helps us to understand. Why some elements are very reactive, hydrogen's extremely explosive, while others, like helium, are inert, don't react with anything. And there are a lot of other periodic patterns we observe in the properties of elements that quantum mechanics explains.